growth, and that leads to exponential growth in general, and this corresponds to the biological scenario of unlimited resources. Okay, and then we looked at how R will change. We consider the simplest declining function, and we consider the linear form of it, right? And this leads us to the discrete time logistic population model.
I think I counted the number of classes that are left before midterm, and so I think yeah, we will have to do it.
Just mute everyone.
So can you please?
Who is speaking there?
Can you please arrange one session?
Who is speaking there? Okay. Messed up my window a bit. Okay, I'm back. Okay, so we have density dependent population growth in this case that accounts for resource limitations, and in this space, in fact, one way to think about this is that this model captures competition within the same species, right? And that's the same species or population is also called the intra-specific competition. And as is very clear now, imagine if we had other biological processes in mind, this function R will change. So, if we had more complex biological processes happening, then you will have a more complex function R. Okay. Then we can write this also in the more compact form. N of t plus 1 is equal to f of n of t, where f basically is r times n. Okay, I have now written a single function r of which is f, and then we can define equilibrium. Equilibrium is a scenario where population doesn't change with time, and if we denote n star as equilibrium, how do we find equilibrium? By solving this equation. Okay, and in terms of R, this is same as solving R of n star is equal to 1. Okay, I hope you all see why this is true, because f is nothing but R times n, n cancels, therefore R n star is equal to 1 is way of finding non-trivial solutions. Okay, okay, so but all the solutions are obtained by setting n star is equal to f of n star. And then we can also, just because a population is in equilibrium doesn't mean it is stable. So to know whether a population is is stable or not, we have to calculate the derivative of this function at the equilibrium and check if the modulus is less than 1. If the modulus is less than 1, it will be a stable equilibrium. If the modulus is greater than 1, it would be an unstable equilibrium. Now, I had actually promised that I will provide you derivation of this, which I still haven't done. So maybe what I can do is at 12 o'clock today, once the plan for today is over, whoever likes, you can stay on, and I will quickly show the derivations for those who are interested. And now let us apply this simple rules to the discrete time logistic model. Someone has unmuted. I request you to mute yourself, please. For the discrete time logistic model, we have f of n is given by r0 times nt to 1. Sorry, I messed up this. 1 minus nt over k. We can do a rescaling. And again, all of you will now remember what the rescaled equation look like. And in the rescaled equation, we can write f of xt is equal to R0 xt 1 minus xt. Okay. Okay, now I will not repeat these calculations because I have done this in the previous class. If you find the equilibrium, you will find that there are two equilibria for this. X star is equal to 0 and X star is equal to R0 minus 1 divided by R0. Now, how do we find the stability? Now, to find the stability, the first step is to find the derivative df over dn. Okay. What is that? That is nothing but d by dn of R0 n. So I'm dropping the t here because it's kind of a, oh, I'm sorry, shall we, so by the way, we can do it in terms of x or n. Shall we just stick to x maybe, because this would be unnecessarily complicated otherwise. Not too complicated, we'll just add an extra factor of k everywhere. So let's do this. Okay, so what would this be? So first is a linear term, that should just be R0. Second is R0x square, and if I take the derivative, that will become 2R0x. And now we evaluate this at the corresponding equilibrium. Okay, so what is this? This is f prime of x. Okay, so let's evaluate this at equilibrium. X star is equal to 0. So we will do this f of the first equilibrium. We are trying to find the stability criteria. So if I now set x star is equal to 0 in this equation, what do we get? We get just R0. Somebody has again switched on their mic. I would really appreciate if you can just mute yourself. Arun, can you just check who it is? Okay, so if f of x star is equal to 0 is R0. So what is the criterion for stability? R0 must be less than 1. Does that make sense intuitively? So the extinction is a stable equilibrium when R0 is less than 1. Does that match with your numerical simulation results? Indeed it does, right? If you go back to previous class, this is precisely what you had told me when you did the numerical simulations using Excel or whatever program you wrote, right? So x star is equal to 0 is stable for R0 less than 1. Conversely, if R0 is greater than 1, it will be unstable. Okay, x star is stable for R0 less than 1, is unstable for R0 greater than 1. Okay. Now let's do the same calculation for another equilibrium. Okay. So what is 0 minus 1 by R0? Now let's calculate f prime. So the first term was, let's now remember what was the terms. R0 minus 2R0 times x. Okay. So it will be R0 minus 2R0 times R0 minus 1 by R0. So what I have basically done is, in this equation, let's call this equation. In this equation, I have replaced x by R0 minus 1 by R0, the value of the equilibrium. Okay. So what do we get? It's R0 minus, these two will cancel. So you have 2 times R0 minus 1. That will lead you to minus 2 times this will be, okay. So this is the value of f star, f prime at the second equilibrium. For stability, what do we need? We need 2 minus r0, which is the value of f prime at the equilibrium, to be between minus 1 and plus 1. Okay. Sorry. I don't think I need to put the modulus when I have already done. Okay. So I hope all of you understood why I wrote this. So the stability criteria was that this modulus must be less than 1. That is same as saying the quantity is between minus 1 and plus 1. Okay. What's page number 4? Okay. So this is the condition for stability, and that leads us to, okay, R0 is, okay. I mean, just do a bit of algebra here. It's very simple. Take the negative sign and then move things around. You will find that R0 is between 1 and 3, which means for this equilibrium to be stable, R0 must be between 1 and 3. Any questions on this?
Yes, sir.
Yes.
So in the previous case, when you took x star equal to 0, fair enough. It is the only stable case when R naught is less than 1. But it is still stable for R naught bigger than 1, right? If our initial population is 0, it's still a stable state. But this equation says otherwise.
What's your name, please?
Oh, okay. Sorry, wait. I got confused. I'm sorry.
Understood now, but it's okay. Maybe this is a question that everybody else may have had. So see, the x. So let me. I think you understood while asking the question what was the confusion.
Yes,
So x star is equal to 0 is true for all values of r0. Okay. Okay, that is true for all values of r0. But I'm just trying to find what is the value of r0 for which it is stable. What is the value of r0 for which it is unstable? So what this analysis in this page has told you is that for r0 less than 1, x star is equal to 0 is stable. And for r0 greater than 1, x star is equal to 0 is unstable. No, unstable doesn't mean that the equilibrium doesn't exist. Equilibrium will exist. It just means that if I make a perturbation, it just goes away. Okay. Meaning if r0 is greater than 1 and if I start with equilibrium 0, it will of course stay there forever. But if I now add a few individuals to it, however small it might be, then what will happen? It will move towards the other equilibrium, which is r0 minus 1 by r0. That's what you find numerically. Okay. That's why it's unstable.
Hello, sir.
Any question?
Respect to like this x star equal to 0, the page 3. Hello? Can you
Yeah. Hey, can you speak up a bit? Also, tell me your name, please.
I'm Rashi, sir.
Yeah, and also, if possible, if your network allows, please switch on the videos when you're talking. It really helps me to know all of you. So, a bit more familiar with the class.
Hello, sir.
Yeah, sure. Hi, Rashi.
Hello, sir. With respect to like the x star equal to 0, why aren't we taking the lower bound also here, like r0 less, like greater than 0 all the time, because we've like designed our model that way, right?
Yeah, so by definition, r0 has to be greater than 0. So I'm not even stating it. So, by definition of the model, we have two constraints. Shall I just state what are those constraints? Okay, so the logistic model, comes with two constraints for okay. So it has the first constraint it imposed on the parameter is that r0 has to be greater than 0, right? Sorry. Okay. Else, in fact, we discussed it long back, right? Populations, we will have unrealistic population value. which is negative values are prohibited, right? That's the first constraint. The second constraint that it has, which I haven't yet told you at all, the following. Again, remember that for any starting value of xt, of course, second, actually three constraints, by the way. We want x to be always positive, right? Okay. Okay, now let's say now I start with x of 1.1. Then this term becomes negative, right? Therefore, the next generation becomes negative. So now there's additional constraint on x. So x equal to 1 is the second constraint to make sure the reason, the numbers we get are reasonable, okay, are biologically meaningful. That's actually a third constraint. Again, it follows from the same reason that xt has to be now between 0 and 1 all the time, or it has to be positive. Now just think about the following. Now let's look at this function. For those of you who are mathematically familiar with the quadratic function, this will be an easy point to notice. What is the maximum value of xt into 1 minus xt? Okay. See, basically xt has to be between 0 and 1, right? In this range, what is the maximum value of xt and xt and 1 into 1 minus xt? So if we just do simple calculus, we will find that the maximum value of xt into 1 minus xt is 1 over 4. Okay, and that happens when xt is equal to half. So this is something I would leave it as a small exercise. And in fact, in some sense, if you actually go to the refresher assignment, I think some question that relates to this might have been there. Okay, so maximum value of this is 1 by 4, and we know that the xt itself has to be between 0 and 1. Okay, so now let us consider xt is equal to half for some reason. Let's say this has now reached a maximum value. So what that actually gives a bound on what's the value of r0. Imagine if r0 was now 5. What will be xt plus 1? It will be will show you weird values, which is negative values. Okay, so basically logistic model to be biologically meaningful, we have three conditions: r0 greater than 0, xt has to be between 0 and 1, and that r0 has to be less than 4, less than or equal to 4. Okay, so now it's possible that some of these may not have fully made sense. I would like you to revisit and do the mathematics bit to make sure you understand this. Okay, and which is also the reason why in my previous class I was restricting you to between to a maximum value of 4. Any quick questions on this? Not necessarily the algebra, but broader points. Okay, so if not, I will now move on, and let us now. So we have found the following, right? So this is called, whatever we have done is called stability analysis. So stability analysis has yielded the following information. At the sake of repeating, let me say that again. X star 0 is in equilibrium, is stable for 0 less than. Okay, so actually we don't know if it is true. I think this is true, so it has to be true. Okay, because the mod of r0 has to be, that's actually fine. And then it is unstable for anything above this region. Okay, and then x star is equal to r0 minus 1 by r0 is stable for r0 between 3 and 1. Now we can plot this, right? Okay, let me plot this now. So x-axis is r0, y-axis is x star. This is 1. Okay, this is again 1. So this is 3. We extend this a bit more. So what have, let's now plot the extinction equilibrium. So it is stable between 0 and 1. Therefore, we draw it with a solid line between 0 and 1. What happens to it after that? It's unstable for all values ordered, all the values of R0. So I will just plot that with a dotted line. And as I told you, 0 to 4 is the only meaningful value of R0 for this model. Okay. Now let's look at this equilibrium. This equilibrium is stable between R0 greater than 1 and less than 3. So up to 3. So what is the value it reaches at 3? It's 3 minus 1 by 3. That will be 2 by 3. So 2 by 3 is somewhere here. So it reaches that value here. So it will look like this. And then it becomes unstable beyond that. So I will plot it like this. Do all of you agree with this? Any questions on this? Based on the stability analysis. Just 2 by 3. Okay. So this is the of how stable equilibria change over time, change over R0, the main parameter and the only parameter in this model. Okay, and then of course you found, did you find exactly this in your simulations? Of course you did find. Between 0 and 1 you found extinction to be stable. Between 1 and 3 you found this branch to be stable, and beyond 3 you found something much more, interesting dynamics. You had a graph that looked like this. I'm going to use a different color now. We had something that looked like this, right? Okay, and then we had something that looked like this, and so on. Is that right? Okay. So now I had mentioned to, let me just say a few things again. So these points where the stability changes, the nature of stability changes is called bifurcation points. And this entire diagram of x star versus the parameter value, okay, and where you sort of demarcate various stability, they're also called bifurcation diagrams, and some people also call them stability diagrams because they basically are showing how the stability of equilibria changes over parameters. Okay, and then okay, now this is a bifurcation point where there is a stable equilibrium that loses stability, and a new branch of stable equilibrium starts, and it goes on, and this new branch has now become unstable, and what you find here is a cyclical, behavior. Okay, now this point is called, because you are going from a stable equilibrium to an oscillatory behavior here, right? And this oscillation in this initial periods were between two values. Do you all agree with that? Is that what you found? Between two values, right? So those are called, two cycle, orbits, two period cycles, meaning, the periodicity of the, trajectories, 2 units, 2 generations. Okay, so this is called a period 2 cycle. And then I think at 3.45, you started finding a period 4 cycle. Is that right? And I don't know how many of you try to find more, by the way, beyond this. Did any of you try to find something beyond these two? Don't tell me you have read. I want to know from others who haven't read, did you try to find anything more on your own after this period 2 and period 4?
So I mean, after 4, there is extremely chaotic behavior, and the model just doesn't work. So
what do you mean by model doesn't work?
as a model, by what I mean to say is that there is no it loses any biological significance it had.
You think it loses any biological significance? Okay,
Yeah,
that's a very interesting statement. Where do you think it loses? Do you think the period to cycle has biological significance?
no, but the population size does, right? NT by K, that ratio does. And so if
What do you
that
mean?
ratio
NT by K is basically
X, yes. So
that's
if
population density. Okay.
yeah, so if X becomes
May I
negative,
know even can you switch on your video if possible?
yes, sir.
Yeah. I can't still see you.
Yes,
Sorry. Okay. Yeah. Thanks.
so what I mean to say is that even if the population density is negative, that would mean that there is a negative population per unit area per unit resource.
What is the negative population density per unit area?
Pardon?
What is the negative population? What is it? You find the negative population?
Yes, I tried running it above 4 at 5.
Oh, we just said
and,
no, 4 we shouldn't know because we shouldn't get a negative population at all. That's a hard constraint.
Yeah,
so we shouldn't really do anything beyond 4.
Yeah, so up till 3 point, after 3.45, it was just chaotic. There was no pattern at all. We tried running it.
Okay, that's good. Okay.
It's random.
Okay. So you thought there was no pattern. Okay, that's okay to know. No problem. Anybody else found anything else? Nilay found no patterns beyond 3.45.
Sir, I think I found the pattern. I'm not sure.
Who is this?
Lakshya this side, sir.
Yeah, can you switch on your video and speak, please?
Sure. Hi, am I audible?
Yeah.
So what I was saying was, the way I was going about it was I was just taking a Fourier transform of the stable range onwards. So after, let's say, 500 steps where I think that it has
You
reached
take the Fourier transform of the time series. Is that what you mean?
Yeah. So I saw like 2-3 peaks arising. So I did not look into it much. Yeah.
For what value? For what value?
For above 3.5.
Which value? Did you choose a specific value? Or did you
Yeah, 3.7, I guess. I'm not sure. I'll have to confirm that. So yeah, so there basically I saw that there were 2 peaks arising, which to me it meant that basically it's like a superposition of 2 different waves. That's why I think 4 stable states are arising.
Okay, fine, sounds good. Okay. So let me tell you, what happens. Beyond 3. Okay. So between I don't remember all the numbers exactly. I'll tell you what happens. Okay, and you should. And I will not be covering much more about this in this course because it becomes extraordinarily mathematical. And as somebody did point out, there are a lot of questions on whether how much of it is really relevant to ecological systems. Okay, so between in the range 3 and 3.45, you find oscillations between 2 values. Okay, and we call that period to cycle. Okay, what does that mean? If you were to plot x versus time, you just find something like this. Exactly, this value and this value will be exactly identical. Likewise, this and this. Okay, and likewise this and this. They're exactly identical. Population is hopping back and forth. Now, this, as we already discussed in the last class, has an interesting implication. Okay, what does this mean? This means that just with intraspecific competition alone, and even in the absence of an external forcing parameter like seasonality and other seasonal, other period temporarily varying, drivers, we actually have population oscillating. So these oscillations are basically some sort of an emergent behavior. So oscillations were not part of. They were not part of the equations we wrote, right? oscillations were not part of the processes we thought of, but this oscillation sort of came about entirely because of internal dynamics. So, which means that next time you see a a periodic behavior in a biological system, you cannot always say that it's because of a periodically varying resource or a seasonality or any such periodically varying factor. But one has to also account for the fact that this may be entirely because of an internal dynamic of the system. So it was a very interesting insight we got from this model. And then in the range, I don't know the upper bound between 3.45, I think 3.54 approximately. Take this with a bit of question mark here because I don't remember the exact range. What you will find is that you will find oscillation between 4 values. And in fact, that's also precisely what many of you, when you were plotting, you found that it was jumping back between 1, 2, 3, 4 values. Okay. There is some range where you will find oscillation between 4 values. Can you now guess what will happen next if we increase R a bit further? Anybody guess? It's a very easy guess. We had period 2 and period 4. What will you expect next? If you just continue this
some odd number cycles. No, they start in some odd number cycles.
Oh, they started odd number cycles, is it?
Like no,
Okay.
I mean, I couldn't see a pattern like you get 3.6.
Okay. So odd numbered cycles also do happen, but if you are within this in the vicinity of where the 4 cycle ends, what you will find is a period 8 cycle. Okay, and if you continue, you will find period 16 cycle, and you will basically find period 2 power n cycle, where for all integers n, every integer value will be represented here. Okay, but what happens is that the range of R0 for which each period, each 2 power k cycle, okay, exists becomes also decays geometrically. Okay, so that makes it very hard to computationally find them. And this entire phenomenon of going from period 2 to period 4, 8, 16, and so on, this is called period doubling bifurcation. Okay, now beyond, I think, in my opinion, beyond beyond period 2, 4, and such measurable values, the biological significance is basically totally lost. Because how do you really even measure period 16 cycle, right? It's going to be incredibly hard because biological systems also have many other factors. Okay, so much of the biological relevance here will be probably lost very soon, as somebody rightly pointed out. But nevertheless, this is a very widely studied phenomenon in the mathematics and physics literature, as an example of how an extremely simple equation. What was its extremely simple equation? Somewhere here, right? Where did I write the equation? I think I wrote it. I don't know where I wrote it. Okay, somewhere here. Okay, this extremely simple equation can produce remarkably complex behaviors. It actually can produce basically all periods. And as Amir was pointing out, not only you will find period doubling 2 power k or 2 power n cycles, you will also find odd number cycles. And basically people have spent careers just figuring out all possible cycles and studying this simple equation, what all complex sort of phenomenon this can produce. Okay, so now apart from the fact that the intrinsic dynamics which had no periodicity, can spontaneously produce periodicity, apart from that part, I don't think there is much we can take from the biological aspect here. Okay, now let's move on. I had asked you one more question in the last class. Okay, so which was for, I think I had asked 2 specific values, 3.6 and 4. Okay, so we had discussed this notion of predictability, right? So what would we think there? we sort of considered this hypothetical scenario of an island where this logistic model is perfectly valid, and there are no other sources of, there are no other factors that influence population dynamics. Only this equation, and this equation perfectly captures whatever is happening. Okay, we assume this, and then we ask the question: is this island population predictable over time? Now, you would naively think that any population which has a deterministic equation of very simple form like this must be predictable. Do you all agree with that? This is basically a deterministic equation. There are no stochastic factors here. There's nothing unknown about this. Okay, and given a value of xt, I know precisely what value of the xt plus 1. Okay, to whatever accuracy you want. So we ask the question: is this island population predictable? And we define predictability in this simple this one, which is we said et is basically x of t minus x of t plus epsilon. What exactly is this? I may have switched the epsilon, by the way. It makes no difference anyway. Where the idea is that I obtain xt starting with some initial condition recursively by applying this, and then I also find xt plus epsilon by starting with an initial condition which is very close to x0 but not quite x0. Okay, so therefore I'll get x1 plus epsilon and so on. So this was x1, x2, let's say we do up to x100, and likewise we have x100 plus epsilon. Okay, and then we find the difference between the two trajectories and we plot them. So what did you find for this? I had asked you plot both xt plus epsilon, and I had also asked you to plot et this time. So what did you find? I haven't actually seen your results. Let me guess what you would have found. If you were in this regime, okay, if you were in this regime between 0 and 3, you will find that this ET will basically decay with time. Is that true for all of you, by the way? This EC will basically decay with time for R0 less than 3. Did you all find this?
Yes, sir.
Okay. Which means that the errors that we make in initially measuring the population has no impact on the sort of predictability of my system over a long period of time. Okay, that means that this is a good sign, right? Now, did you do the same graph for xt is equal to 4? What do you find if you do the same graph for xt, rt is equal to 4? Sorry, what did you find?
It doesn't die out to 0.
It doesn't decay to 0, right? Did anybody find the decay to 0? I hope no one did. So what are the implications of this? First of all, was it did you make sure you have made no mistakes? You make sure there are no mistakes. Like if so, if you are convinced this is correct, what's the implication?
For these values of R, very small deviations in initial conditions. Small for value of R that is equal to 4, some small deviation in initial condition could lead to very different outcomes.
But will lead to, right? Okay, now what does that mean? It basically means that it has very little room for let's say you really wanted to project how certain insect populations change over time, and because maybe that insect population is a huge pest, let's say, and Amir goes and measures some current population density, and you have this equation that perfectly for this system, and then Nilay goes and makes the same measurement. They come back with let's say a measurement difference of, let's say, 1%. Okay, but now if you're both asked to make projections for how the insect populations will change over time, therefore we can prepare for pest management. Would your prediction concur, or will they be dramatically different? They will be dramatically different, right? So even though we knew everything about the system, our conclusions will be dramatically different. Okay, so this is despite the fact that we had a deterministic system. Deterministic system, extremely simple equation, right? When it's hard to think of something simpler than quadratic. Of course, we have a linear equation, but there we know we only get exponential growth or decay. Okay, and despite these two, what we find is that system lacks predictability, and this phenomenon is also called deterministic chaos. Okay, so we use the word chaos very sort of loosely. So the word chaos basically means that the small differences in the initial conditions can lead to sort of exponential divergence in the trajectories, and therefore even extremely simple systems are very difficult to use for making predictions. And another classic example that's sort of often used is that in fact one of the very first systems where the chaos was sort of discovered was in the context of weather systems, climatic systems, actually weather systems, not climatic systems. There people wrote down 3 equations and found that even this very simple 3 coupled equations can lead to what exactly the same type of behavior, where small initial condition differences can lead to very different outcomes. This meant that the weather is extremely hard to predict over long times. Okay, and then that's why there's this famous sort of analogy that people give, right? Sort of a butterfly fluttering somewhere across the continent can sort of lead to tornadoes somewhere else, right? Halfway across the globe. So the basic idea is that smallest initial conditions can lead to very dramatically different outcomes, and therefore just because we have very simple equations that govern the dynamics doesn't mean that we have predictive power in these systems. And a lot of this happens because of 2 reasons. One is the fact that these systems are non-linear, right? So they have this non-linearity. In this case, the simplest form of non-linearity, which is quadratic non-linearity. Okay, so and the same implication that holds for weathers also, if these kind of models are true, will also be applicable for biological systems. Now, this also presents a very hopeless scenario for modelers, right? Or in terms of for somebody, if as a modeler, let's say you have made this statement that even if your biological system is extremely simple, hey, look, you can never make any predictions. Now, it's actually both beautiful in some sense, such a simple model can lead to such complex dynamics. At the same time, it's also a bit hopeless, right? That means, how can you really hope to understand something more complex? What if I incorporate much more complex behaviors that actually happen in biological systems, right? So it presents a hopeless scenario in terms of being able to model and make predictions in biological systems. Okay.
So currently, whatever this COVID case is also like that, right? There were so many predictions. Then there is a second wave. That we don't know why it happened. So it kind of, puts all this modeling into, so many questions. And I don't. I just tried to connect these things. That it's when you said it is hopeless. I could really relate to it. So
yeah, absolutely true. In fact, so there are modified versions of this model that are applicable to spread of infectious diseases. And in fact, there is actually evidence that some signatures of chaos can be found in how some certain aspects of dynamics of diseases as well. Okay, but you're absolutely right. Broadly speaking, using models to make predictions can be quite a hopeless sort of scenario, except that in the much of the, but we also need to understand that when we think of cases like infectious diseases, the part that is actually most useful is the initial part, right? I know the initial part, these models unambiguously say, independent of the details of the disease, that the growth will be exponential. Okay, and just like we have this R0 in this model, there is a corresponding R0, right, in the disease models.
Yes.
Is that right?
Yes.
So here it corresponds to, what does the R0 here correspond to? A given individual in the current generation, how many offspring that this fellow, this individual
Infects.
leads to in the in the population models, it's just the number of offspring, right? Whereas in the case of diseases, it's the number of
Infections.
individuals that the currently infected individuals will cause in the before this fellow actually. In fact, the knowledge, R0 is almost transportable. The definitions are almost nearly transportable. Yeah, but the much of the measures and everything is based on the fact that we have this extremely exponential growth that's very hard to control. Okay, but how exactly the decay happens, that's a much more harder problem to predict, because human behavior comes into picture, policy decisions influence them. So all those factors now become much more harder to sort of model in a very precise way.
Yeah, thanks.
I had another observation from the previous page 7, where when we found that when epsilon was really small, even when R0 was greater than 3, it would vary a lot, and then it would stabilize at 0 in the end.
Okay, yeah. So that's possible, absolutely. If you are in the if you are in the periodic oscillation regime, okay, because there is predictability in terms of periodicity, right? So you would expect that the ET will eventually decay down to 0 for small enough epsilons. You're right. But it is also possible that they might just become out of phase. So the XT trajectory and the XT plus epsilon trajectory, they will be exactly out of phase, imagine, right? In that case, the ET will not go to 0, it just becomes a constant value, which is the difference between the two values that the population is oscillating.
Right. And that I saw was like you mentioned, you see oscillatory behavior like XT and XT plus epsilon being out of phase, and even this error also shows oscillatory behavior.
That's also possible, especially when the higher cycles happen, right?
Yeah.
More than 2, 4, 8, and so on.
Yeah.
The both trajectories will settle down to some periodic,
yes.
But in fact, they will have this exactly same periodicity, right?
Yes.
But depending on how exactly the out of phase they are,
you
will also find an oscillations in ET.
Yeah, and for even for R equals 4, I found for 10 power minus 18, you get error 0.
Error 0, but the 10 power 18 minus 18, your computer will not be able to handle.
I guess. Yeah.
I mean, unless you have set it to double floating precision, it probably can't handle, right?
Yeah.
I think 10 power minus 10 is when you can, beyond which you can't really trust how well it's handled. Okay, so I don't know how many of you notice this. Imagine if you start with an epsilon of 10 power minus 10, how many generations does it take you for the trajectories to diverge? I would it's an interesting exercise to try actually. Even a difference of 10 power minus 10, you will realize that it doesn't take too many generations to actually have an error of the magnitude 0.1. See, as soon as you have a magnitude of error of around 0.1, you are pretty much lost, right? Because the maximum range here is between 0 and 1 anyway, right? Once you reach 0.1 error, the difference between two trajectories, you are as good as having entirely different trajectories. So try with epsilon of 10 power minus 10 and see what happens. It's actually very interesting. How quickly it actually the smallest error also sort of magnifies over time.
Sir, I had a question about chaos.
Yeah.
Sorry.
Yeah, please go ahead. Yes.
Is chaos?
Is Yukta, is it?
Yes, sir.
Yeah.
So is chaos a property of the models which we try to create, or is it something that can be there in a natural phenomenon too?
That's a great question. So there has been a lot of research on whether chaos really exists in real world populations. So the Fridays lab basically so far what I have covered is, more on the mathematics side, right? So in Friday's class, what I will try to do is I will try to give you an assignment where I will sort of force you to think, to sort of make connections between whatever we have discovered in this setup so far, in this model setup so far, and how do you make sense of this empirically. Okay, so I will give you some assignments in the direction, but the short answer to your question is that yes, there are some biological systems where people have found signatures of chaos, but those are really, really small.
Okay.
And there are many, many
Okay, sir.
challenges associated with, actually finding chaos in real systems. I will, in fact, ask you as a part of, Friday's lab to sort of think more on those lines. So Friday's lab this time will be entirely on, making connections with empirical data. Okay. What are the challenges that you will face, and how would you go about, resolving them? And they're all very, very non-trivial questions. In fact, many of the questions we will, were only saw last, I think, in the early 2000s and so on. So any other questions? So if there are no more questions, I want to go back and quickly show how to derive the stability criteria. Is that fine? And whoever needs to leave can leave, by the way, and you can watch the video later on. This will take about 10 to 15 minutes. It uses some mathematics, and many of you will be familiar with, which is basically Taylor series expansion to sort of arrive at the stability criteria. Okay, so I will go to that now. And from next week onwards, we'll start the continuous time models. Okay, so let me now sort of quickly do derivation of stability criteria. Okay, so the derivation actually uses the intuition of what is stability in a very rigorous way. Okay, so what is stability? So we have an X star, which is equilibrium, and we find that by solving this equation. Okay, so what is stability? Stability is when a small perturbation dies. Okay. So if this happens, we say X star is stable. Okay, so let us do this now. Let's say I have now made a perturbation to an equilibrium. X star, let's say, was the current value. The system was in equilibrium, and I have made a perturbation delta X. Let me use the capital X. To this equilibrium, let's say I have now made a perturbation. Let's say this is the value. So X star was present at, let's say, time 0. At X1, I have forcibly made this perturbation. In fact, we can call it X0 itself. So current time is 0, and X0 is X star plus delta X. I have made some perturbation X0. So we want to know what is X1. So how do we say a system is stable? If X1 is closer to X0 than X0 itself. So X1 must be closer to X star than X0 was. Okay, let's now write this graphically. Okay, this is X. Okay, this is, let us say, value of X star. And then I have basically made this perturbation delta X. So this is how far I am currently from the equilibrium. Now what happens? We want to find what is X1, right? So X0 is here, which is X star plus delta X. We want to know what happens to X1. If X1 is somewhere here, that means it is stable. Do you agree? Let us say X1 was, let's say X1 actually is at a value somewhere here. Let's say x1 was here. If x1 was here, then that means it's unstable. Graphically, do you all agree with this? Graphically, do you agree? We started here. After one generation, if the system came closer to the equilibrium, it's a stable equilibrium. But if it actually went further away, it will be unstable equilibrium. Okay. So let us now try to find out what is x1. How do you find x1? x1 is nothing but f of x0. All of you agree with that? That's a by definition, right? That's our model. To find x1, just input that into the function f and we will get the next population. But what is x0? x0 is nothing but x star plus delta x. Okay. So now we are going to use a trick called a Taylor series. I hope Tanveen had sent a video on how to make sense of Taylor series. So I won't be not covering that. What is Taylor series? The idea of Taylor series is that, if I know value of a function at x star, I can use that to find the value at a nearby location. Okay, so according to Taylor series, I can write down and it's basically infinitely long series. So if I know the value of f at x star, if I know the first derivative of f at x star, if I know the second derivative and so on and so forth, I can exactly find the value at a nearby because that's what we are looking at. A small x is small. So far everything is fine. Any questions up to this? Okay, there are no questions. Let's do the next step. So we have assumed that delta x is small, right? So think of delta x as something like 0.01. Okay. So then the value of this will be 0.01 times some value here. How much will this be? This will be 0.01 square. That's 10 power minus 4. So therefore, this number will be substantially small. Okay. And this will be 10 power minus 6, even smaller. So what we're going to say is, let's ignore all of these terms. Let's assume they are all basically like 0. And with that assumption, what we can do is we can write is that fine? So therefore, x1 is nothing but this. Okay. So any questions before I go to the next page? Okay, no questions. So remember that we have this now. So because x star is in equilibrium, it follows this. Okay, and then so far we have shown that okay. Now let us use this equation 1a in 1b. Therefore, I'm going to replace this by just x star. Okay. So then what do we have? x1 is approximately equal to x star plus delta x times this. Okay. And then let me now write down, take x star on the left hand side. So what we have is x1 minus x star is equal to delta x times. Okay. So what is this? Let's go back to the previous equation and look at this diagram. So x1 minus x star is the new difference between new distance to the equilibrium, right? So x star was the initial distance to the equilibrium, and x1 minus x star is the new distance to the equilibrium. Is that fine? So we can write this as delta x at time 1. Okay. So therefore, what we have is delta x at time 1 is equal to delta x times f prime of star. What this equation now tells you is how is the perturbation growing over time. I started with the perturbation of delta x, it now became delta x1. So perturbation has become delta x1, and how did it become? It basically got multiplied with this factor of f prime x star. So what is our interest? We want the perturbation to die. For perturbation to die, should the multiplication factor be greater than 1 or less than 1?
Less.
So for perturbations to die, the multiplicative factor f prime of x star must be less than. Okay, so which basically leads us to the condition of stability. Okay. Any questions on how we arrived at the condition for stability?
A question.
Yes.
Yeah. So here we assumed basically we ignored the higher order terms of the Fourier in the Taylor series, right? Hello.
Yes, yes, very yes.
Yeah.
Very
So,
big,
but so like so the result depend on that assumption, or is it true otherwise also?
yes,
Even
it does depend on the assumption. So therefore, this criteria is also called. So let me box this criterion for stability. It's also called linear stability analysis. So it is valid only for small perturbations. So if you did make a large perturbation, this analysis cannot tell you what's going to happen. So it's called linear stability analysis. Sort of intuitively thinking about this, one way to think about this is, is this actually a local stability? It doesn't tell you whether it's globally stable. Okay, I hope I understand the words globally stable and locally stable. Okay, and in fact, in the next class, I will introduce an analogy. In the next week or so, I will introduce a analogy called landscape. So imagine there are this huge landscape, or you think of a bowl with only a single bottom, single minima. So if a ball is rolling in that, if there is a single minima in the entire world, if this bowl is as big as the entire world, and if there's only single minimum point in the bowl, how much ever perturbation you make, it will always come back to the minimum, right? But how, so in that case, that such a minima is called a global minima. Okay. On the other hand, imagine a bowl which has multiple minima. Okay, so something like this, lots of undulations like you see in real mountains, real landscapes, right? So depending on how much perturbation you make from a bottom of a valley, it may come back, or it may also go to a new valley in that landscape, right? So therefore, in that case, there are multiple stable states, and linear stability analysis tells that only if you make small perturbation, I know you will come back. I can't tell you what happens if you make very large perturbations. So linear stability analysis holds true only to check the local stability. So this is good for identifying local stability. It doesn't tell you about the global stability of a system. Any more questions?
Shouldn't that be mod delta mod?
Yeah, that's a great question, because if I go back to first page, or maybe the second page, I said that the criterion is mod less than 1, right? Now, Can one of you tell me where does the mod come? I have proven only one side of the stability. Okay, where does the mod come from? Maybe just look at this and think about this.
If your delta x was negative through the other side, maybe.
Okay, exactly. Yeah. So the thing is, just think about what was happening numerically between 2.5 and 3 when you are simulating the logistic model between R0, 2.5 and 3. You found these oscillations that decayed, right? So what was happening there was this. So what was happening in those cases was I made a perturbation, okay, and the perturbation would not just decay here, it would actually decay to this part. It jumps across the equilibrium. Okay, when you jump across the equilibrium, what is important is not the jump you made, the length of the jump you made. You still have to check whether this distance versus this distance. Okay, which one is, whether the new distance, which is the mod of distance between x star and the new location, whether that was actually larger or smaller than the old distance. If you account for that, you will actually also find that the other sign will come up. So basically, the other way of saying it is, this is not necessary, by the way. This is fine here, but it's not necessary. An alternative path is that f prime of x star is actually less than 0 also, but greater than -1. If this is true, what would have happened is that not very far away. I would still be closer in compared to the previous situation. Okay. So if you now put these two together, you get the mod. This and this together, you get the mod. Is it clear? Is the intuition behind this clear? Any other questions? Okay, so I will just stop here then. So if there are no more questions, so I'll see you all on Friday. Thank you. Bye.
Thank you.